Hi guys, so this is what's known as a related rate problem in calculus, and it's solved by using kind of something called implicit differentiation. We don't have to go into too much of those details, but we have a ladder that's 10 feet long, and it's leaning against a wall, and the bottom of the ladder is 6 feet away from from the wall, and it's moving out at 4 feet per second. So meaning this bottom of this ladder is moving out at 4 feet per second this direction. So to the right, so that's 4 feet per second. And at this particular point in time, when it's exactly 6 feet, and the question is, the top would be falling down. And so, how fast is the top falling down? So, that's what we're trying to figure out. And typically, for a lot of these problems, what you usually do is, if you can, try to draw a picture. So you try to draw a picture and label anything that you know, and anything you don't know, just come up with letters that you can just label, and then you try to use some kind of fact in math, either something that's self-evident or some geometry property to connect the unknown quantities. And for related rates, you usually end up taking the derivative of both sides of that equation with respect to time. So let's see, make a little bit of a room for ourselves. And what I did was I labeled, and let me, so that we keep this, we know this is 4 feet per second. And so what I did was I just labeled the horizontal to be X and the vertical to be Y. You really could have used any symbols. And the length is fixed at 10, and that's actually going to be important that it's fixed at 10. So the thing about it is, so what we want, so what do we want? In terms of Y, now that we have that, we want to know how fast is that dropping down? And that's really in terms of calculus. If t is time, and for these problems, you pretty much always consider t to be time, the derivative of y with respect to time, that's what we want. And we have that x is 6, and we also have that dx dt. It's going in a positive direction, which is 4. Notice it's going in a positive direction, but y is decreasing, so hopefully we'll end up with a negative answer for dy dt. And notice it's kind of implicit. This is a right angle, so this is a right triangle. So one of the first things that would be helpful to know is to know what y is. And we can apply the Pythagorean theorem because the sum of the squares of the legs should be equal to the square of the hypotenuse, which is the side opposite the right triangle. So the Pythagorean theorem, and this is something that you just almost kind of expected to know. So x squared plus y squared is equal to 10 squared. That's the hypotenuse, which is 100. And we know that x at this point in time is 6. So 6 squared is 36. So 36 plus y squared is equal to 100. So we can solve that for y by subtracting 36 from both sides, solving it for y squared. We get y squared is 64. And the solution is y is plus or minus 60. Sorry, y is plus or minus 8. But the problem constrains us here because we don't have negative lengths. So y here must be 8 at this point in time. Okay, so now what else can we do? So in general, so that's how to find y. But how can we find a relationship between dy dt and dx dt? Well, if we take this equation here, and I'm going to rewrite it, 100, take the derivative of both sides. So we're using the chain rule, and we're assuming that both x and y, they're functions of t. So this is actually a composition of two functions. You're taking the function of t, which gives you x, which is its position at any point, and then you're squaring the result. So whenever you have a composition of functions that take the derivative, you use the chain rule. And so the chain rule says take the derivative of the outside function, multiply it by the derivative of the inside function. And we're using that symbol for the derivative of the inside function. And similarly, y is also a function of time. So it's the same thing there. And here's the tricky part. What's the derivative of 100? Well, 100 is a constant function. Think about 100, it never changes. So a constant never changes with time, and therefore its derivative must be 0. And now, what do we want? We want dy dt, right? That's what we want. So keeping in mind, this is one quantity, this dx dt and this dy dt. They're just our fancy way of writing the derivative of x with respect to time, the rate of change of x with respect to time, the rate of change of y with respect to time. And so if we want a dy dt, let's move this whole term. So we're adding two terms. We can move this to the other side and it becomes negative. So 2y dy dt is now equal to negative 2x dx dt. And let's see here. So I'm going to just go to my next slide here, and 2y dy dt is negative 2x dx dt. So I'm just going to copy that down here. 2y dy dt is negative 2x dx dt. So at this point in time, what do we know? We know, so we have everything. And really, if we divide both sides by 2, those 2's are going to go away. So we can just ignore those. And we have x. We know x is 6. We have dx dt because we said it was going at 4 feet per second, right? And we have y because we solved that for y and we found y was 8. And we don't want to forget the negative. So we've got everything there but dy dt. So now this just becomes a simple matter of, so 6 times 4 is 24. And now we can solve for dy dt by just dividing both sides by 8. It is negative 24 over 8. So it's a division problem, and it's 3. And because the signs are different, it's a negative 3. So it's a negative 3 feet per second. So the ladder is falling at 3 feet per second. And you would write that out. You wouldn't necessarily have to say negative because it's implicit in the word falling. So the y value is changing at negative 3 feet per second, but it's falling at 3 feet per second. So that would be the answer. And like I said, most related rate problems are similar to that. You just have to come up with you're usually establishing a relationship between variables at a certain instant of time, but then you need a general form for how the derivative of one value relates to the derivative of another. And most of them usually follow a similar pattern. So thanks a lot. And if you like the video, please subscribe to the channel, hit the like button, and stay tuned for more.